Hello students, myself ms.Divya, Amble, assistant professor in Gokhale College, Kolhapur. Now we are going to start our paper number 7th, real analysis second. Okay. Now we are going to start our first chapter, sequences and operations on sequences. So see, sequence. Definition of sequence is: sequence is a function whose domain is a set of natural number and codomain is a set of real number. In the previous semester we have already seen what is function, what is codomain, and what is domain. Okay, so see next, sequence is usually denoted by this curly bracket sn n equals to 1 to infinity, or this triangular bracket sn n equal to 1 to infinity, or simply curly bracket sn. Okay, and nth term of sequence is denoted by Sn, means first term is now in terms of n, we can put n equal to 1 2 3 and so on. So first term of sequence is denoted by S1, second term of sequence is denoted by S2 and so on. Okay, so see now some examples of sequences. First sequence is sequence Sn is equal to n square. Okay, now instead of n we can put here set of natural number which is 1 2 3 and so on. So now if we put n is equal to 1, then we get 1 square is 1, next 2 square is 4, next 3 square is 9, next fourth square is 16, fifth square is 25 and so on. Okay, so see next sequence is sequence Sn is equal to 1 upon n. So now if we put n equal to 1 2 3 and so on, what we get? First term is 1 upon 1, which is 1, next 1 upon 2, 1 upon 3, 1 upon 4 and so on. So see next sequence is sequence n upon n plus 1. Now if we put n equal to 1, what we get? 1 upon 1 plus 1, which is 1 upon 2. Now if we put n equal to 2, then what we get? 2 upon 2 plus 1, which is 2 upon 3, next is 3 upon 4, 4 upon 5 and so on. Okay, next sequence is sequence Sn is equal to minus 1 raised to n. And now if we put n equal to 1, then what we get? Minus 1 raised to 1 is minus 1. Next if we put minus n equal to 2, then what we get? Minus 1 square, which is 1. Next minus 1 cube is minus 1, next minus 1 raised to 4 is plus 1 and so on. So what sequence we get? Minus 1 plus 1, minus 1 plus 1, minus 1 and so on. Okay, so see next sequence is sequence Sn is equal to, which is a single element, that is 1, means this is the constant sequence. Okay, so what sequence we get? 1 1 1 and so on. Okay, so see next, subsequences of sequence. See definition: let capital S is equal to Sn be sequence of real numbers and n is equal to sequence ni, I equals to 1 to infinity, be subsequence of set of natural number, then the composite function S composite n called subsequence of S. Okay, and defined as S composite n of I is equal to this small 0 means what? Composition. Okay, this is not actually 0. So S composition n of I is equal to what? S of n of I, means we have to put here bracket in terms of composition. So what we get? S of this capital n of I means what? In this capital N of I, what numbers we can get? Ni. Okay, as per sequence. And then this S of n of I means what? Sni, means simply subsequence of sequence means what? If we take set. Okay, and now we have already seen that subset of a set, which is similar to subsequence of sequence. Okay, so see here, hence composition means what? S of, so what sequence we get? S composition of n, means in the sequence S composition n, what elements we get? S of n of I. Okay, means what sequence we get? S composition n is equal to curly bracket Sni, I equals to 1 to infinity. Okay, means we have to remember in the composition we get sequence S N I, where I equals to 1 to infinity. Okay, that's it. So this will clear by example. So see first example, if S is equal to sequence Sn is equal to n square and capital N is equal to sequence Ni is equal to 2i minus 1, where I belongs to set of natural numbers, then find S composition n. Okay, so see solution means we have given S, we have given n, and we have to find S composition n. Okay, so see solution given, we have given S is equal to Sn is equal to n square, where n equal to 1 to infinity, and n is equal to ni, which is equal to 2i minus 1, and I belongs to set of natural numbers. Okay, hence subsequence of sequence Sn will be, now we have already seen the definition of subsequence. So what we get is composition n is equal to sequence Sni, I equals to 1 to infinity. Okay, and now we have given the sequence Sn, which is what, Sn is what, n square. Okay, so Sni will be what, Sni will be ni square. Okay, now we put S in terms of Sni, we get ni square. Now also we have given ni, so what is n, so what is ni, ni is 2i minus 1. Okay, this is we have given. So now if we put, so in place of ni we have to put 2i minus 1, so what we get, 2i minus 1 square, I equals to 1 to infinity. Okay, means now if we put I equals to 1, then what we get, 2 into 1 minus 1 square, which is 1. Now second we have to put I equals to 2, then we get 2 into 2 minus 1 its square, which is 9. Next 2 into 3 minus 1 its square, which is 25, and so on. Okay, so we get the sequence as composition n is 1, 9, 25, and so on. Okay, so see next example, if S is equal to sequence Sn is equal to root n equal to 1 to infinity, and capital N is equal to ni, where I raised to 4, I belongs to n, then find S composition n. So similarly here also we have given sequence S, sequence n, and we have to find S composition n. Okay, so see solution given, S is equal to sequence Sn is equal to sequence root n equal to 1 to infinity, and capital N is equal to sequence ni, which is equal to I raised to 4, and I belongs to set of natural number. This is we have already given. Okay, so now S composition n will be what, by definition Sni, which is equal to, now we have given here Sn, which is root n, so Sni will be what, root ni, and also we have given this ni is equal to I raised to 4, so what we get, under root I raised to 4, which is equal to I square, and I running from 1 to infinity. Okay, now if we put I equal to 1, then we get first element 1. Secondly, if we put I equal to 2, then we get 4. Next 3 square is 9. Next 25, 16. Next 25, and so on. Okay, so see next example, if sequence S is equal to sequence Sn is equal to 1 upon n equals to 1 to infinity, and capital N is equal to ni, which is equal to 2 raised to I belongs to n, then find S composition n. So similarly here also we have given S, we have given n, and we have to find S composition n. So see its solution given, S is equal to sequence Sn is equal to 1 upon n equals to 1 to infinity, and capital N is equal to ni, which is equal to 2 raised to I belongs to n. So S composition n will be what, by definition we know it's Sni, and we have given Sn is 1 upon n, so Sni will be what, 1 upon ni, and also we have given ni, which is equal to 2 raised to I. Now if we put ni equals to 2 raised to I, then what we get, 1 upon 2 raised to I equals to 1 to infinity, means which is what, 2 raised to minus I is equal to I equals to 1 to infinity. Okay, so now if we put I equals to 1, then what we get, 2 raised to minus 1, which is 1 upon 2. Nextly, if we put I equals to 2, then what we get, 2 raised to minus 2, which is 1 upon 4. Next, 1 upon 8, and so on. Okay, so see, next example is, if s is equal to sequence Sn n equals to 1 to infinity, which is equal to 2 into n minus 1, n equals to 1 to infinity, and capital N is equal to ni, which is equal to I square, I equals to 1 to infinity, then we have to find S composition in next S5, S9, N3, Sn3, and next is we have to check whether n is subsequence of sequence k equals to 1 to infinity. Okay, so now see, we have given sequence S is equal to Sn, 2 into n minus 1, n equals to 1 to infinity. So you can see here in the second question, we have to find S5, S9, means S5, S9 are what, elements of sequence Sn. Okay, S5 means fifth element of sequence Sn, S9 means ninth element of sequence Sn. So here we have to find first sequence Sn. Okay, so now if we put n equal to 1, then what we get, 2 into 1 minus 1, which is 1. Next, 2 into 2 minus 1, which is 3. Next, 2 into 3 minus 1, which is 5, 7, and so on. So in the sequence Sn, first element is S1, second element is S2, next S3, S4, and so on. Okay, so like this we have to also find sequence n, which is which is ni, and we have given it is I square, I equals to 1 to infinity. So what sequence we get, 1, 4, 9, 16, 25, and so on. So in the sequence n, first element is n1, second element is n2, next n3, n4, and so on. Okay, so now we have also given the sequence k equals to 1 to infinity. Okay, k equals to 1 to infinity means this sequence will be what, if we put k equals to 1, then 1, next 2, 3, 4, 5, 6, and so on. Okay, so now we have to find that 3 questions. So first is what, S composition n, and by definition we know as S composition n is Sni, which is equal to, now we have given what is Sn, we have given Sn is 2n minus 1, so Sni will be what, 2 into ni minus 1, and also we have given ni, which is I square, so what we get, 2 into I square minus 1. Okay, so what sequence we get, 2 I square minus 1, I equals to 1 to infinity. Now if we put I equal to 1, we get element 1. If we put I equal to 2, means 2 into 2 square minus 1, which is 7. Next, I equal to 3, 2 into 3 square minus 1, which is 17. Next, 31, and so on. Okay, so see, now S5 means what, fifth element of Sn. So Sn is what, 2 into n minus 1, so 2 into 5 minus 1, which is 9. Next, S9 means ninth element of sequence Sn, and sequence Sn is what, 2 into n minus 1, so 2 into 9 minus 1 is, which is what, 17. Now n3 means what, third element of sequence n, which is I square. So if we put I equal to 3, then we get 9. Next, we have to find Sn3, means what, third element of sequence S composition, and which is 2 I square minus 1. So if we put I equal to 3, then we get it 17. Okay, now here we have to check whether n is the subsequence of k. So what we have already, sequence n is 1, 4, 9, 16, 25, and so on, and also we have given sequence k is 1, 2, 3, 4, 5, 6. So you can see here n is a subsequence of k, means what, all the numbers of n are included in k, so n will be subsequence of k. Okay, so see, next definition is limit of sequence. Okay, let sequence Sn be a sequence of real numbers. So we say that sequence Sn has the limit capital L if for epsilon greater than 0, this symbol is what, epsilon. If for epsilon greater than 0 there is a positive integer capital N such that mod of Sn minus L is less than epsilon for all n, for all small n greater than or equal to set of natural number. Okay, so we can say that sequence Sn has a limit capital L if this condition is satisfied, which is what, mod of Sn minus L is less than epsilon for all n greater than or equal to capital N. Okay, also another definition is what, if sequence Sn n equals to 1 to infinity has limit L, we can write limit n tends to infinity Sn which is equal to L. Okay, so here we have two definition for limit. First is, we can say that sequence Sn has limit L if for epsilon greater than 0 there is a positive integer n such that mod of Sn minus L is less than epsilon for all n greater than or equal to capital N. And secondly, second definition is, if sequence Sn has limit L, we can write limit n tending to infinity Sn is equal to L. Okay, so see, next definition is convergent sequence. So see, if the sequence of real numbers Sn has a limit L, we say that that sequence Sn is convergent to L. And if sequence Sn does not have a limit, then we say that sequence Sn is divergent sequence. Means if sequence has a limit, okay, if sequence has a limit, then we can say that that sequence is convergent. And if sequence does not have a limit, then we say that sequence is divergent. Okay, now the next points will be seen in the next lecture. Thank you.